I'm not sure I've ever seen Christian either.
Why don't we go ahead and get started? So for those in the room, good afternoon. For those on the Zoom, good morning, good afternoon, and good evening. Welcome to the BoF called Emerging Challenges for HPC System and Facility Electrical Distribution Systems. I know it sounds like a mouthful, but it's all about electrical power, electricity. We all know how important that is in our lives, and obviously also for HPC and supercomputer systems. Couple reminders. The first one, this session is being recorded. I don't know all the ins and outs. I know it'll be put into the hub at some point and it'll be out there for a period of time. So if you want to watch it again, or you have colleagues that want to go see this session, this BoF, totally up to them. The second thing, for questions, for those that are on the phone, or I guess on Zoom, or even in the room, if you want to sign into the hub, you can ask question there. You can do it through the Zoom chat, or in the room. If you want to ask in person, by all means, raise your hand. You can ask a question from where you're at. We'll repeat it. Or if you would like, you could come up to one of the microphones here. We'll just make sure we have our masks on and you can ask the question so everyone can hear it. So as we get started here, we have, as you can see, our distinguished group of panelists that are, most of them are remote. Brandon is here in the room. I think it represents a good cross-section of the HPC electrical power sector. What I'm going to do is have each of the panelists introduce themselves, and you'll hear a little bit about them. So I'm going to start with Brandon here in the room.
Hi, my name is Brandon Hong. I work for Lawrence Livermore Lab. I am an electrical design engineer. I help design the distribution from basically the grid down to the computer systems, normal systems and up to advanced technology systems.
Okay, thanks, Brandon. So Grant, you can go next.
Yeah, hi everybody. Grant Stewart from Los Alamos National Laboratory. My title there is Project Director for Utility Operations. And LANL is a little bit unique in that we operate transmission and distribution and have on-site generation. And so we operate as really a full-blown utility and have a number of supercomputing centers within our grid control. Welcome to the meeting.
Good, thanks, Grant. Okay, Christian.
Hello, everybody. My name is Christian Blug. I'm working at Siemens in Germany as an electrical power engineer for more than 20 years. And I am actually principal key expert for power quality analysis and department head for power quality and earthing studies at Siemens PTI. A significant part of my work are grid connection studies, which are also dealing with connection of large data centers to the public MV and HV grids.
Okay, good. Thank you, Christian. Rob? If you're talking, Rob, we don't hear.
I had to unmute, sorry.
Okay.
This is Rob Rongstad at HPE. I'm a power architect. I'm basically responsible for power from the wall to the compute blades. I haven't done much at the grid level, but interested in this topic.
Okay, good. Thanks, Rob. David?
Hello, everyone. Good to be here. My name is David Mohr with NVIDIA, distinguished engineer focusing primarily on power within the data center. So really looking at everything from the blades out to the utility is going to be my focus.
Okay, good. Thank you, David. And I'm Joe Prisco, the moderator. I'm a senior technical staff member with IBM. I focus on electrical power in data centers, all the way up to power supplies and even some of the front end sections until you get past the bridge rectifier and then also the active PFC sections. After that, it gets too deep for me. So to kick things off, I have a couple questions for the panelists that we'll go through. But by all means, if you have questions, at any time, let us know. So I'll start off with question one. One of the main challenges with HPC systems is the large power fluctuations over a short period of time and its impact on the electrical distribution. Is this one of your challenges? And if yes, please explain the specifics of this challenge to the audience. If there is another recent or current electrical power distribution, power delivery, or power consumption challenge you dealt with in HPC systems or data centers, we'd like to hear about that. So Christian, I'll go ahead and start with you on the phone to explain a little bit more about this type of question and what your thoughts are with the voltage fluctuations.
Okay, thank you, Joe. As a power engineer, I'm looking to the data centers from the point of view of a grid operator. And grid operators, they have to guarantee a sufficient power quality for all their clients. And therefore, committees have defined compatibility levels for evaluation of power quality distortion, and they are defined within the grid standards. For example, IEEE 519 or IEC 61000, or in Germany, we have the VDE RR 4110. And in those standards, limits are defined which have to be fulfilled. For example, with respect to voltage frequency, and especially low and fast voltage changes. And these are the voltage fluctuations, or also flicker if we are talking about the impact on bursts, and of course harmonics. And sources of big distortions are not allowed to be connected to the grid, and this could be interesting in the future for HPC. Because considering the growing power consumption, the impact of HPC on the power quality should be known, from my point of view, in a very early phase of the planning or extension of the plan. One has to know the value of the maximum and minimum load. Of course, you have to know the power factor under different operation conditions. You need to know the harmonic content, and most important from my point of view, the change rate of the power, which has a direct impact on the power quality, not only for your internal distribution grid, but also for the upstream public grid. You should be aware that, for example, in Germany, such big loads should only produce a voltage deviation of 2, 3, or maximum 5%. And this could be an issue, especially when you are exploring a larger power consumption in the future. So therefore, I would recommend that everyone who want to expand in these power ranges should perhaps be aware of these issues, and from my point of view, also simulations of the impact of HPC on the public grid with the help of digital models should be considered.
Okay, good, Christian. Yeah, thank you very much. Good input. So what I'm going to do is I'm going to ask the other panelists for what their thoughts are on this. So I'll start with Brandon here in the room.
Yeah, there's many different aspects that we have to cover. And one of the difficult parts is for upcoming exascale systems, we are unsure of a lot of the characteristics. Still developing, like right now I have a system arriving in a year and I don't have those full characteristics yet. So we can model as much as we can of what we know, but a lot of it is still in the development for more of the cutting edge systems.
Okay, good. Thanks, Brandon. Okay, Grant, like to hear your input.
Yeah, thanks, Joe. Just to add a little bit to what Christian said and some other areas of insight, the growing requirements of any load in a system are important to plan for. But we, at our site, we've seen, particularly explosive growth in the demand for the computing systems, and that it's difficult to cover that sometimes, because when you're a system designer, you're really more likely to say what the maximum peak power demand is, but it's very likely only going to happen in rare events. And so to invest, the full amount to provide that peak for a system is very expensive, and the time required to develop the power supply path is equal or greater than the time to develop the compute system itself. And so we really have a dilemma in this industry to provide enough power, but not overdo it. We often talk about the grid niche of a given HPC system in this conversation, and one of the things we mean by that is, how stiff is the grid, or what's its ability to its impedance path and the ability to provide high short circuit current. And these are sort of sometimes event driven things and require lots of analysis that Christian was beginning to talk about, and that we've talked about extensively on our panel. For LANL, we try to take it with a grain of salt a little bit, but we're sometimes surprised by how much peak demand can occur with a new system, even with all the math and analysis and conversations and design that goes into it. So this is quite a challenging subject. Thank you very much. Happy to take any questions about that.
Okay, good. Thanks, Grant. So Rob, what are your thoughts?
I agree with what Grant was just saying. A lot of the systems that we design, the processors have a certain TDP power. Say, the chip itself is 200 watts, but they spec a peak power of 2x TDP. Well, when you got a system that's got thousands and thousands of these processors, if they all go to 2x TDP at the same time, trying to design for that pathological peak power is really difficult, and as Grant mentioned, very expensive. If you have to design for that theoretical pathological peak power, it gets very expensive. To get to the question, is this one of the challenges that we've seen? And to me, it's to date, we really haven't seen this being an issue at the distribution level, at the grid level. But we keep putting bigger and bigger systems out there, and at some point it probably is going to hit that problem, hit the point where the grid cannot react. So
Okay, thank you, Rob. And then last, David.
Yeah, so at NVIDIA, we've ran into this a little bit. We'll call it a problem, but it's kind of hard to describe yet, because I don't think we've actually measured anything at the grid level that we can say where we put things out of bounds. But there is a growing concern as we increase the size of the supercomputers and add more and more silicon to the cluster, what that profile is going to look like. So completely agree with the other panelists that we need to have better modeling tools, anticipate where the energy is going to be needed, and how we can adequately provide it without overloading the grid. Or, if something goes wrong, how badly can we affect the grid locally?
Right. Yep. Excellent points, David. Thank you. And when I think of this problem, just in general with power fluctuations, and I try to keep things simple for those, especially not electrical engineers, many of you remember some of the older big vacuums. As soon as you would turn on that motor, the lights in your house would flicker a little bit, right? They go dull until they get back. Well, basically what you're doing, as soon as you turn that on, you add this load, you get a little bit of a voltage sag. Now take this for these data centers at, 100 times, 1,000 times, and that could be the magnitude of the problem. There were a couple of comments online that I would like to read, because I think they're very relevant. And if any of the panelists have any comments, one of them from Adrian Jackson: we recently have had issues with voltage drops from the grid because of supplier issues. The interesting thing, because of supplier issues. The interesting thing is some systems can cope and some can't. Another comment was that power fluctuations seem to matter less at installations that have a mix of HPC systems. Individual fluctuations hide in the noise of a larger mix of HPCs. Any thoughts from any of the panelists on these comments?
Well, if you'd like, I can take a crack at that.
Yeah, please, David.
So based on my experience, the mixed environments, I'll say, appear to be a little bit cleaner. It's just the nature of different power supplies, different distribution. The workloads are not generally correlated. Then if you when you look at an infrastructure that is just one large supercomputer using all the same racks and all the same power supplies, and it's running a singular workload, all of those things align. And I don't want to put it as it becomes the worst of the worst, but every little idiosyncrasy within the power system seems to be magnified. So that is certainly something that I have run into, that mixed environments appear to be clean. A dedicated environment, you have to be more cautious and plan for these alignments.
Right. Excellent, David. Yeah, diversity of loads. I definitely agree as well. All right.
I'd
So
like to chime in. This is Grant.
Yeah, please, Grant.
I could take a moment. For the comment. Sorry about the dogs. If you're already experiencing voltage sags at your site, there's a lot you can do to work on that condition, but it doesn't bode well for adding a large new supercomputer if you're already in that condition. So you want to get with your service provider, and you want to make sure you have a consultant that can help you, that can work with a dynamic model, and start to understand what are some things you could do on your end, and what are some things the utility could do to improve service, and maybe you can partner on a rate structure for that. But you're gonna find that you have some impedance limitations on the path for your power flow that you have to work on. So I'm sure you could hire Siemens and Christian are certainly capable of that kind of analysis, but there are many firms that can help you with that. It does get expensive though. Thank you.
Right. Yep. Good. Thank you, Grant. All right. So we'll go ahead, unless there's any other input. We'll move to question number 2. Now, this is the type of question I always like, because it's more about what keeps you up at night. I know as engineers, a lot of times we're so busy with all these things. Sometimes when we're sitting there in the evening or laying in bed, you're noodling, thinking of stuff, and all of a sudden you just become maybe concerned about something, and you're not sleeping too well. I know Brandon mentioned exascale computing, but I'll go ahead and read question 2. With exascale computing on the horizon, what are you most concerned about as you plan and prepare the HPC electrical ecosystem for the next generation of IT equipment? If your biggest concern is large power fluctuations, how do you plan to manage that? So for question 2, give all the panelists a chance to respond. I'm going to start with Brandon here in the room.
Okay. Yeah, it's a little going back on one more example, but so just a real life experience right now from our site. And we're a square mile over at Lawrence Livermore Lab. Our HPC facility is only a portion of that. And when it was first built 2004, and we only have a 12 megawatt building, and everything is down to 208 fed off little panel boards off the wall. As systems progress, some of the advanced technology systems we're running into 480. We beefed up the building up to 45 megawatts currently, but now we're looking at the huge exascale block loads, right? So I think as mentioned about the sort of the mix of the HPC centers, it applies to some areas, but for us, we're gonna have huge block loads. So we're adding another 40 megawatt feed just for our building. The physical nature of the building staying the same, and we're shoving all this power into it. We're having to go from more industrial and commercial solutions using panel boards, and now into utility solutions where right outside of our building, we have a large 40 megawatt switch yard. So it's causing us to have to talk to the utility provider a lot more. Before, we only scheduled slow maintenance days, known outages, but now we have about like a 40 megawatt load that's coming in 2023. And then after that, potentially 2 exascale systems running at the same time in 2027. So that's the big block anticipated load coming. And these swings are going to be a huge impact to what we have upstream. So in doing that, and the aspect of designing it, installing it, we're involving the utility, getting in the design phase, and in getting in that relationship with them. They see that this block load's coming. We actually are switching in 2023 from like a smaller zone connection point on the grid to a larger one. So if we do have those fluctuations, it's a smaller impact on the overall grid. And it's subject to a lot less variations.
Okay, good. Thanks. Thanks, Brandon. So Grant, what are your thoughts?
Well, I agree with everything Brandon said, of course, but I'd just take it in another sort of direction here. We spend a lot of time trying to partner with our high performance computing and make provisions to serve their long-term growing load. But with the recent passage of the Bipartisan Infrastructure Act and our federal, in the United States at least, our federal goals of achieving zero carbon, electrifying the fleet, and trying to achieve zero carbon in facilities, the grid, the demands on the grid are growing, not just from supercomputer, but from these other factors at a very accelerated pace as well. So when we thought previously we had planned the major investments necessary to provision the grid to supply fully the power that we expect to grow into from HPC. Now the denominator has changed yet again in a fundamental way. So you always have to be ready to do some more analysis, and you can't really expect it to be, one big investment is going to take you through. Surprises happen, policy changes, and it's a very dynamic situation. So I'd say that's what keeps me up at night, thinking about how all of that comes together. Thank you.
Perfect. Good. Thank you, Grant. All right, Christian.
I see 2 points. The question which you are asking, the biggest concern, the large power fluctuation, how do you plan to manage that? And if this is a question to the HPC operator, then it would be very interesting for me if you are able to control the load, especially to control the change rate of the power. This is from my point of view, this is the only thing what the plant operator can do. And as Brandon already told, all other aspects have to be discussed in a very close cooperation with the grid operator. You have to decide to which voltage level you have to connect. And this would also mean, let's say, more invest, perhaps in cables, in substations, perhaps also in a step-up transformer.
Right, exactly, Christian. Good, thank you. Okay, Rob?
Sure. So, at HPE, we're actually deploying exascale level systems today. And so part of the things that we've done to try to mitigate any of the power fluctuations is to try to design the system so that it meets like the semi F47 power curves, or the the IEC power quality. So that's what we've done from the load side. And what Christian mentioned, what is the slew rate? I'd be interested to see at what point does that get to be a problem for the grid? How many 1,000 amps per microsecond, or whatever that number is. That's something that I've got some telemetry that kind of looks at it, but at a pretty slow rate. We collect telemetry at like 1 hertz, so we can't see real fine slew rate, on that current. But at what point does that really become a problem at the grid?
Right, yeah, that's a great question. Great question, Rob. Good, thank you. So last but not least, David.
I would break my concerns into 2 areas. So the first one would be normal operation, where we should be able to control the ramp up and the ramp down of the cluster, just to be able to, I'll say, adjust it for whatever constraints are within the infrastructure, all the way out to the grid. What I'm most concerned with is when something goes wrong. A workload suddenly crashes and we're going from very high power to very low power almost instantaneously. That's going to just bounce everything throughout the infrastructure, and that's the one that really, I would say, is keeps me awake at night, trying to come up with what's going to happen and what can we do about it. So that's the piece that I don't have a good answer for on how to manage, is that sudden release from the load, and where do we go with that energy? What happens to the over voltage? The grid release causes a local voltage spike, and that just transfers through the entire system. So that's the one that I'm most concerned with.
Got it. Yeah. So we have both voltage sag and voltage swell. So yeah, excellent responses. So there's a few questions that did come in through the hub, and I'm going to I'll get to most all of them. I think this one actually is really relevant to this question. Why is no one addressed approaching their utility to collaboratively address the challenge? Their decision space includes moving loads to stiffer voltages. And I think that's very relevant to what we're discussing here. Any of the panelists want to respond?
Yeah, that's something that we've done at Lawrence Livermore, and we have talked to the utility, and they have, and we're already on a stiff grid to begin with currently, and they are switching us to a larger, like basically a pool, right? And so we're a really small sliver of the pie now, and won't be as big of an impact.
Okay, good. And then Grant, like to hear your input on that question.
Yes, sir. Thank you. I would like to bring attention to a paper that the Energy Efficiency Working Group published a couple of years ago, where we we canvassed quite a few HPC operations and characterized by a few different specific topics. What was their relationship like with the utility? What kind of rate structure were they in? Is it time of use? Is the rate affected by the time when it's consumed? And what are some provisions for adding load, and how does it work? And that's available through the high performance computing working group webpage, I believe. I'm sure you can follow up with Natalie Bates, the lead for that organization. And I would say that I'm not aware of an HPC that isn't working with their utility provider and in that conversation to some extent, but it's exaggerated. Yeah, Natalie just put that on the share on the chat. So it's exaggerated for sites that make a big jump or that might be in a situation where they're more on the end of a long power line than in a really integrated grid in a major city. So you have all kinds of different situations. So you can't just take a one size fits all approach to any part of that. You have a very unique circumstance. You have to work with your system that was evolved over a period of time and a number of separate investments, and you start from where you are. Nobody gets the luxury of putting a brand new HPC system somewhere, or that seldom happens. I know data centers are doing that, but we're usually with HPC, usually strongly aligned with an academic or research-oriented program, and so you're kind of limited on where you can move things. So a lot of facets to that. Maybe
Right,
that was
right.
one. Thank you.
Yeah, good, Grant. Yep, all excellent points. Thank you. Any other panelists want to respond? If not, I got a few more to go through.
Joe, I want to answer on the question, why cannot a utility make the grid more stiff? This is very complicated, yes, very complex thing, because if you want to have a stiffer grid, then you have to invest into cables, you have to invest in large transformers, and you have to invest in more generators in the grid. And the planning in the distribution or transmission grid is a long-term planning. You have to coordinate this with other measures. And therefore, if you're, for example, Brandon is saying he needs 40 megawatt within 2 years, then it's very hard for the grid operator to provide a stiffer grid within 2 years, because this will make a conflict with his long-term planning things. That's
Right.
that's the big problem.
Exactly. Good, Christian. Thank you. So there's one of the comments I want to read that was in Hub, which I think is actually very relevant, a great comment from Ahmad. We work on analyzing the power consumption by HPC. One challenge that we see is data quality from the sensors. Large number of gaps in the data cause issues in the analysis, modeling, and prediction. I think that's a very relevant comment. Any of the panelists want to comment on this?
Yeah, this is Rob. I would agree with that. In the HPE equipment that we have, we've got basically telemetry coming out of every voltage regulator, every rectifier, and so we collected it. It's if you collect from even a small system, you get gigabytes of data in just a matter of minutes, and trying to wade through all that and validate it. So theoretically, if you add up all of the power that's coming out of the VRs that are actually feeding the chip, add that all up, that should equal what's coming out of what's feeding it. And a lot of times it doesn't. And so either either somebody's lying to you or something is missing. And trying to validate the accuracy and the validity of all that data that's coming in gets very challenging.
Yep, fully agree. Fully agree with that. Any other thoughts from any of the other panelists?
Well, this is Grant. I would just add that for one of our recent systems, we had all the telemetry gathering data and feeding at a very short time step, and it was very important to the commissioning of the system. And at some point after things were up and stabilized, we really couldn't afford to continue to just migrate all that data into storage and use it. So it was turned off at some level, and then following after the commissioning, well into the operations phase, a few months ago we had an event where a whole bunch of like X of Y PDUs went tripped offline, and we had unfortunately turned off the telemetry, so it was really hard to decipher the origin of that problem and to go back and try to recapitulate or model it. So it's a dilemma. What do you do with all that data? How long do you leave it in your system? And can you make effective use of it? Thank you.
Yep, good. Thank you, Grant. All good points. And
Yeah.
I go ahead. Anyone else want to?
The lab, we have utility meters doing all of our main incoming feeds, but as all these systems are coming in, what we're doing is doing more more feeder breaker metering, sub-metering. One of the difficult parts of that is though you have all different companies and manufacturers and trying to integrate that into a similar database. One big purchase does help that out, but just integrating existing equipment to go along with the new stuff it's been pretty difficult.
Okay, good. Thanks. Thanks, Brandon. There's actually where we moved in the questions for the panel. So if you have some, you're welcome. If you have any in the room, please ask. I got a few more to go through online, but if you do, just raise your hand. And again, we'll work with you. So a question, another one from Adrian is a follow-up to the sensor data question. And this is a really good one too. What DCIM software solutions are people using? So we just talked about, data and gaps and what we need to do, but what are you currently using? So Brandon and Grant, what do you use in your data centers to collect the sensor data?
I'll chime in. Or Christian, were you gonna talk? Well, okay, I'll chime in and share that at LANL, our largest machines are operate in a classified environment, and so the monitoring data can't flow outside of the envelope for our system, and so we have utility data that's more of like in the open, and we have internal system data that resides internally, and when you want to decipher some of these power events, you need to have carefully synchronized clocks, and you need to look at waveform capture, and it becomes pretty difficult to decipher the root cause of events and therefore conceptualize what improvements are necessary. So that we have that unique challenge too.
Okay, good. Thanks, Grant. And thinking of it from the other angle, from the equipment standpoint, perhaps Rob or David or Christian want to comment as far as capabilities of IT. What information can be extracted, and how would you extract that through what protocols, or Redfish, or what would you suggest to be compatible with DCIM?
At HPE, we're using a Redfish API to collect all of the data. That's something that we just started in the latest generation, one of the redfish format.
Okay, thanks, Rob. So David, Christian, any thoughts from your end?
Agree that the redfish, that type of approach is becoming more common. Looking at it more from the hardware and infrastructure perspective, it's been made, the comment was made that a lot of the VRs feeding the CPU, GPUs have that capability. And I think at that level, the high resolution, those VRs have that capability. And then moving out to the next step, like an AC to DC power supply, also has that capability to monitor its input and output, maybe not at the same resolution. Again, going through the infrastructure, utility meters, either at a tap box or a panel box, can have that capability as well. What I see is the further away we get from the silicon, the chips, the resolution seems to get a little bit worse. And we're collecting more and more information, but it just doesn't have either the resolution or the accuracy to really help us out in some of these events. So that would be a focal point, is to be able to coordinate, like another comment, the timestamps. How do we collect all this information into something useful?
Right. Yeah. Great input. Good. Thank you. And there was a comment also, which I think is very applicable from Adrian. I know people use Sunbird, but it's quite expensive. And I know, just when I'm familiar with some different packages like Nlight and some other ones, there's so many DCM software solutions out there. It's almost like you have to pick one and stay within the bounds of that. So another question online, which I know is near and dear to basically everyone on the panel, or at least I know ones who have been involved with the HPC working group. What are the challenges to commissioning the electrical infrastructure for a large HPC facility? Have you seen liquid-cooled IT simulators load banks? So I'd like to hear really everyone's input on that. I know we've had a lot of great discussions within the work group. So I'll start with Brandon here in the room.
Yeah, so we're having that 40 megawatt switch yard installed along with a brand new cooling tower. So we are, for the cooling, we are bringing in load banks. There's actually the vendors on site today, so I'm missing that meeting, but they're coming out there to bring out load banks. We'll commission them that way with a false load. But as far as the electrical, there's no real way that we're doing it yet. And we'll have the cooling tower and the mechanical equipment on that switch yard. We will need to maintain at least a 10 megawatt base load on that to make sure the switch yard stays in operation. But one way that actually I visited Lawrence Berkeley Lab, and what they've done is they commissioned putting load banks on smaller, down to the feed to the exascale computers that they're going to connect to the exascale computers, and tested each branch load. It seemed very beneficial, especially with the infrastructure of the racks that we're going to be receiving for exascale. So I think we could go down that far, but as far as the large mechanical loads, we are bringing in, I think 5 megawatt load banks to commission those.
Okay, good. Thanks, Brandon. So Grant, what are your thoughts?
Well, I think with a load bank, you can simulate steady state power. It's a little more difficult to simulate a dynamic pattern or event, and try to understand, are you adequately commissioned for the dynamic events? And I think I've learned a lot from my conversations with Christian about the way you overcome that is you build an adequate power model, and then you commission to the model settings. And if you have an adequate model with the right resolution, time step, and it's analyzing for all the right performance criteria, the ride through characteristics of your devices and so on, you commission by verifying that you're set up according to the model. And that should be good enough. And you can't actually physically simulate the condition that we've sort of postulated, framing this conversation today. Christian, I would invite you to elaborate further if you have any more on that.
Yes, I agree totally. We are also involved in such studies, and especially dynamic and transient behavior has to be simulated in a very early stage. For this, you need, of course, the load characteristic, but also the characteristic of the events like capacitor banks, or let's say if there are generators, to get a good picture of the dynamic reactions of the events. But this is normal task during, let's say, designing and planning of such a plant. And with such models, you can not only simulate, let's say, the dynamic load behavior, but you can also simulate the impact of faults, external or internal faults on your power quality. So, and therefore the usage of simulation models is very common. Also to make the design and finally the grid robust against disturbances or sudden load changes.
And if I could just add one more thing to that, Christian, the other thing that I think about a lot is the contingencies. We design these plants so that you can maintain any major feeder, any major switchgear, and any major transformer. And Murphy's Law comes into play. The weirdest condition is going to happen when you're in an off-normal configuration, and so you have to commission to be able to, for your system to be able to operate through all those contingencies. So you got to have a bunch of what if analysis in your smart team to dream up those contingencies that you need to model, and sometimes all of them in dynamic mode too.
Exactly. Mm-hmm.
Right. Yeah, exactly. Yeah, very good comments. So Rob, David, any thoughts on HPC electrical commissioning?
My only thought there is, Christian mentioned having to do all this very early in the process, and normally I think that the customer's designing the plant well before HPE as the supplier has hardware that they can test to provide them what the load's going to look like. And a lot of times we can do some simulations, but trying to simulate thousands and thousands of nodes running in parallel to be able to provide the customer, this is what the worst case dynamic load is going to look like, again, is a pretty challenging problem. So I think it's kind of a chicken and egg thing. We don't really know what the load's going to look like until we stand it up on the floor and start running things.
Right. Yeah. Very good point. Very good point.
Yeah, I really agree with what he just stated, that so many times we're building all of this as we're simulating it, and sometimes the site is a little disconnected from the supercomputer being built. HP is separated from its customer. NVIDIA, we're off doing other things. We're maybe a little separated from HPE. So I think it's a learning process for all of us, and I encourage everyone to share their results and collaborate so that we can learn from each other and try to prevent some problems that we will all be sharing in the future.
Yes.
Right. I can't agree more with that. Just bring all the right experts together from all ends of HPC, from utility to the owners, operators, data centers, to IT equipment providers, and everyone in between. Good. Thank you. Another question that came in through the chat, and again, a really good one. I think these are really good questions. Have you seen issues with large utility transformers operating at small loads, resulting in electrical resonance, / voltage swings? So anyone want to, on the panel, want to take that? I'll read it again, just so you make sure you heard it clear. Have you seen issues with large utility transformers operating at small loads resulting in electrical resonance voltage swings?
Yeah, and at Lawrence Livermore, we have not. And currently, we shared our site with other programs. So the existing switch yards are not impacted by low loads, but we will have that potential with our own dedicated switch yard. But that's why we do need to maintain that minimum that was posted by the utility or required by the utility.
Okay, good. Thanks, Brandon. Any other thoughts? Go ahead.
Yeah, I've had an experience, and I wouldn't identify it necessarily with the utility transformer, but an installation that was being commissioned. All of the IT gear, the cluster itself was at very low operating power points, realistically below its minimum because there was actually nothing loaded. Everything was connected, but had no intelligence yet. So there was an oscillation, really distorted high PhD within the infrastructure itself because the power supplies within the IT were operating at a very low power factor, very light loading. Once a little bit of workload was put into the environment, the power factor did come up and was corrected. Whoop, there goes my background. See, real live issues.
Yeah. That's a good point. Besides, go ahead, Christian. I think you're in a response.
There are several kinds of resonances. The one which you were addressing are perhaps a resonance which is initiated by, let's say, some small harmonics. And you have to know that the resonances depend on, let's say, the capacitors, inductances, and the loads. And that's exactly what is happening here. If you are increasing the load, then you are adding a resistance to this, and resistance are damping. That's the point. And you also have to know if you are running capacitor banks in parallel to your grid. This will has also influence on resonance effects. So one has to know if you are talking, let's say, about ferroresonances or harmonic resonances. But of course, they can resonances can depend from the load situation at the grid.
Right. Yeah. Excellent point. It just reminds me back in the day when we used to add we would add resistance and inductance by increasing or decreasing length of line cords to help with some resonant points that we would encounter. Yeah. That's funny. Ted took me back there.
This is Grant. I just want to chime in a little.
Yeah, please, Grant.
Someone in the chat mentioned power surges, battery, kind of fishing in that category. And I was just thinking about at the LANL site, we have some large modest generation in the 25 megawatt kind of range, and we have power system stabilizers and automatic voltage control. And then separately, we have what's called a static VAR compensator. That's and together those devices provide some dynamic support and voltage stabilizing that is above and beyond what a typical tap changer transformer system with fixed shunt capacitors would have. And so I guess there are more advanced remedies for the more advanced kind of problems like that. They just take that planning time and the big investments as you build. So there are certainly remedies for those kinds of problems. And you're going to have to, just knowing that is a potential is a good place to start.
Right. Yep. Excellent point, Grant. Thank you. Any questions in the room, by the way? All right. Seeing none, I have one more from Adrian. And this is another really good one. Is there a significant difference between an HPC center and a cloud data center from a power perspective? So anyone on the
Yes,
panel want to take that?
I
Christian?
think I can answer. Cloud data centers, they have a very high power consumption. We are talking about 120 megawatt or more, but they have a very heterogeneous load characteristic. So the dynamic of the load is much lower than the dynamic of a HPC. And this is the major difference from the perspective of, let's say, from the grid.
Right. Yeah. Excellent point. I was thinking of the same one, Christian. Anyone else want to chime in on the panel?
Just not so much of a power perspective, but money perspectives. As our site, our power bill is so low, where using the cloud, the rates are just not comparable, so it's not really an option.
Okay, good. Thanks, Brandon.
I'd like to chime in. I'm not an
Sure.
expert in the area, but, or really any area, I guess, but I've been hearing that some of the advances in cloud computing with, artificial intelligence and some of the other challenges are moving cloud computing load characteristics more in the direction of the kind of loads we've been talking about for HPCs. So maybe Christian was right about how they've been historically, but they may be coming closer together in the future.
Yeah, Grant. Yeah, it's a good point. Time will tell. Because when I think of cloud, and I also think of, the hyperscale, it can be one and the same depending on how you define it. But yeah, the same thing. You have thousands and thousands of servers and compute, and how they're being used. We'll see in the future how it differs from HPC. Right now, I think there is a difference. Like Christian had pointed out, HPC tends to work more in unison, where at least with hyperscale and cloud, you have all these individual servers that are operating by themselves, essentially, with satisfying user requests. So we are just about out of time. Is there any last minute questions, or better yet, from the panelists? Is there anyone from the panel that wants to make any closing comments before we end the session? All right, well, what I want to do is I want to thank everyone in the room for joining, everyone through Zoom. Enjoy the rest of the conference. Have a good rest of the day, and safe travels home, and thank you.
Thank you, Joe.
Thank you.
Yeah, thank you.
Thank you for hosting us, Joe.
Sure, yeah, no problem, David. Thank you, guys.